Welcome back to our course on fluorescence spectroscopy, principles and applications. Today is part 4. We're going to talk about frequency domain time-resolved fluorescence. It's very similar to what we spoke about in the previous lecture with time-correlated single photon counting. It's an alternative method of measuring the time-resolved decays. So let's just take a look at the two methodologies. In the pulse or the time domain, which we spoke about last time, a pulse of light is used to excite the sample, and from that you can calculate the lifetime or the multi-exponential lifetime, whichever it is. Phase modulation or frequency domain fluorescence is similar, but it's done in a completely different way. Instead of using a pulse of light, it's done with a modulated light beam. And the light beam has to be modulated rapidly because it's going to be measuring nanosecond decay times. And what the experimental observables is the time delay of the fluorescence is measured by the phase angle, and the demodulation of the fluorescence, that is a decrease in the peak to peak height. And we'll describe those in considerable detail. But let's just consider what the same measurements would look like in the time domain and in the frequency domain. In the time domain let's assume we have a single protein, has two tryptophanes in it, one's on the surface, one is buried. We add some quencher that can decrease the lifetime of the exposed tryptophan, but not the hidden tryptophan. So what we have after the addition of quencher is not the initial 5 nanoseconds, but we now have a mixture of 5 nanoseconds and 1 nanosecond, which is a multi-exponential decay. And we know that in the time domain, this looks like a curve for the log of the intensity versus time. What does it look like in the frequency domain? Well, it looks completely different. What we have instead of time is the frequency, which is the frequency at which the light is modulated. And let's look at what the two decay times would look like. A single exponential 5 nanosecond decay time would have that characteristic shape, with the phase angle increasing with frequency and the modulation decreasing with frequency. A 1 nanosecond decay time would look the same way, except it was shifted to higher frequencies. When you have the mixture, the shape of the frequency response is what changes. And in the frequency domain method, we use the shape of the frequency response to recover the intensity decay law of the sample. Let's look at what the two data sets look like in the time domain and in the frequency domain. This is the time-dependent decay of NADA, N-acetyltryptophanamide, which has a single exponential decay. As you can see, it has a pretty lousy impulse response function. It was done with an older photomultiplier tube. And there's two lines here, which is the measured number of counts and the calculated decay. And the deviations are around the bottom. And we expect a chi-squared about 1 for good fit. In the frequency domain, the data, in a sense, they look the same to me because I've done this so much, but perhaps not to you. In the frequency domain for NADA, we see a phase angle that is increasing with frequency, see a modulation that is decreasing with frequency. The dots are the data, and the line is the fitted curve. And underneath that, we have two deviation panels because we have two types of data. We have phase data and we have modulation data. So we plot those two deviation plots, and from that we calculate an over all chi-squared, which is the goodness of fit parameter, which looked pretty good for this. So nada is a frequency, is a single exponential decay, but it's good to see the two data sets side by side. Let's look at the frequency domain measurements in more detail. Just to point out that this is the phase angle. It reaches a maximum of 90 degrees. It never knows it goes beyond that. These are the modulations, the peak-to-peak height of the emission, and that starts at 100% and goes all the way down to 0%. And the deviations are calculated by the least squares method that we described previously. What are the equations linking the intensity decay law to the phase and the modulation data? Now, you might not have seen these equations before, but they're moderately simple. One thing we have to remember, it's easy to get this mixed up, is that the frequency that is always, the frequency down here is actually the modulation frequency in hertz. The frequency that is used in all of the equations is the frequency in radians per second, so it's 2 pi times the frequency. And by the way, this square root should have gone all the way over the top of that. But anyway, the law is the tangent of the phase angle. This value is equal to the frequency in radians per second times the lifetime of the sample. The modulation equation is a little more difficult. It's 1 over the square root of the terms you see here. So I cannot give you an intuitive explanation as to why these equations exist, but these are the correct equations, especially for a single exponential decay. Now, why have these measurements not been done until close to 1970? Well, it's difficult to measure the phase and the modulation of an 80 megahertz signal. The signal, here's a time scale here for the 80 megahertz signal for what 5 nanoseconds is. And there's the incident light, and the phase you see is delayed in time. In order to measure this, you'd be measuring, a couple of nanoseconds. And the modulation is decreased, as we'll explain later, by the form of the intensity decay. And remember, this was done before 1970, and the electronics really weren't available. Maybe they were available someplace, but were not readily available to researchers. The modulation is described as it's a ratiometric measurements of the modulation of the incident light divided by the modulation of the emission. So in order to, people had performed measurements like this in earlier publications, but this was difficult to do. And the thing that made it really very simple was cross-correlation detection. And this is something that was developed by the, I'll say the Marconi people, by the radio technology in the 1950s. And they figured out how to mix a high frequency signal with a low frequency signal, with a high frequency signal that is just slightly different in frequency. And the result of that gives you a low frequency signal that is easy to measure. So notice the time scale here is milliseconds rather than nanoseconds. Here we have a 50 megahertz signal that is mixed with a 50 megahertz signal by 25 hertz. As you might imagine, you need pretty good frequency synthesizers to do that, and that's not the way it was done in the 70s but today we can buy such good frequency synthesizers. And the beauty of this is exactly the same information is contained in this 25 hertz signal that was contained in the 80 megahertz or 50 megahertz signal previously. Now you have a lot more time to measure, milliseconds rather than seconds. Another advantage is the 25 hertz signal is a pure sine wave. It's not easy to get a pure sine wave in these high frequency signals, but this coarse correlation method, the second generation of it, made things into pure sine waves. And the thing that I like the most is that many cycles of the high frequency signal contribute to each one of these low frequency phase and modulation measurements. And I think that's something that provides great accuracy. The mixing is done in the photomultiplier tube, where a signal is put into the last dynode that modulates the current at 50 megahertz plus 25 hertz. And it's absolutely magical how this works. It works easy enough. I actually soldered the wires together in my lab to do this, and I'm not known for any expertise in electronics. So what did we have prior to 1970? Prior to 1970, the instruments operated really at two frequencies. They were frequency typically 10 and 30 megahertz. So here we have a trip repressor that was mutated, but we're only going to look at the data for the wild type trip repressor. And note that if we were able to measure the entire frequency response, it would be relatively complex. What was done in the 70s is you would measure this at two frequencies, and you would get what I would call apparent phase lifetimes and apparent modulated lifetimes. And it was virtually impossible to reconstruct the entire frequency response, or let's say it in another way, it was impossible to reconstruct the entire time response just using these two frequencies. This actually caused quite a bit of confusion because at a single frequency, irrespective of the complexity of the decay law, you can always measure an apparent phase lifetime, which is whatever you get from the sample. Remember, you don't know what this is when you're measuring it. Or you can get the apparent modulation lifetime, and you don't know what the rest of it is. And this actually corrupted our thinking for a large amount of time, because we used to talk about things in terms of the phase lifetime and the modulation lifetime. And I guess this is a warning to, certainly I've fallen in this trap several times in my life, where you call something the wrong thing and you proceed on looking at those particular values when in fact they're going to confuse you because they're composites of a lot of different parameters. So now we tend to talk more about the phase, the actual values at a particular modulation frequency. What does a variable frequency instrument look like? It looks very similar to what we discussed in lecture number 2, where we discussed instrumentation, and it has a module where you put in the sample. The reason for a turret here is because it was an easy way to get the impulse response function by comparing the scatterer to the actual sample. One of the differences in the instrument is we had to get modulated light. Back in 1970, they used a rather cumbersome acousto-optic approach. By the time we got to 1983, we could use an electro-optic modulator, which was a lot more stable. Frequency synthesizers were available, and I was actually shocked that they worked so well. you set this high frequency, 100 megahertz, whatever it is, and set the other one plus whatever frequency it is. And by and large, when you put it into if you do the cross correlation of the phototube, you get the phase and the modulation at the lower cross correlation frequency. And to this day, it's still something that surprises me, and I can't explain to you in any direct way. I'm sure, well, if I were an electrical engineer, I could, but let's just say the cross correlation works. These instruments worked up to about 200 megahertz, which was adequate for many applications. At this stage, in 1983, time-correlated single photon counting was still in the flash lamp stage. You might remember from the previous lecture how the flash lamps were several nanosecond pulse widths, and they were not very nicely shaped. What limited us to 2 megahertz, it's limited by the modulator and the phototube response. That was changed later, but it doesn't affect the basic principles of the frequency domain method. So let's look at the few measurements of single exponential decays rather than that complex decay we looked at previously. So we used two compounds, anthracene and non-cyanoanthracene, and we looked at their frequency responses. And it looks like the proper shape for single exponential decay, and of course it fits as a single exponential decay for about 12 nanoseconds. The anthracene had a shorter lifetime, around 5 nanoseconds, and because it had a shorter lifetime, the frequency response is shifted to higher frequencies, but it's exactly the same shape. And you can see from these curves what I mentioned earlier about the max phase angle being 90 degrees and the modulation eventually going to 0 if you could go to a high enough frequency. One of the interesting things that has not really been taken advantage of yet is, you might remember in single photon counting, you're using 100 laser pulses and you're collecting 1 photon. In these phase fluorometers, the photon flux is not limited to single photons. The number of photons impinging on the phototube can be orders of magnitude larger than for time correlated single photon counting. So there's no such thing as a limited photon count rate, but of course you have to stay within the limits of what the phototube is able to respond to. But this larger signal level is important. And just as an example, sort of a biochemical example, for the collisional quenching of the molecule sp(q) by chloride, as you increase the chloride concentration, the lifetime goes to shorter and shorter values, starting at 25 nanoseconds, which has a crossover point around 10 megahertz. But if we get to higher chloride concentrations, we're down to, excuse me, an order of magnitude less, 2.7 nanoseconds. And you'll notice all the decays remain single exponentials. They're just shift along the frequency domain. And the high number of data points provides very good resolution of the decay time. And we actually use this to, in the later experiments, detect transient effects in diffusion. But that's off topic, but it took advantage of the high signal to noise of the frequency domain measurements. So how do we analyze a multi-exponential decay? So we did a simulation here with 2 fluorophores, 10 nanosecond fluorophore, these are all simulated values, and 2.5 nanoseconds, which is shifted to higher frequency. And then we did a simulation where we had a mixture so that half of the fluorescence intensity came from the shorter lifetime, half of the intensity came from the longer lifetime. And we use this as a test, we use this to recover the multi-exponential decays. You'll notice that this goes to a very high frequency here. This is something that's available in some labs, but most labs are limited to the 200 megahertz range. So how do we do this fit? Well, we do it just like we did it in time-coded single photon counting, which we look at the deviations of the decay for any model. So if we assume a double exponential model, we'll get a very good fit. Now let's look at the goodness of fit parameter, the chi-squared. You might remember we only had one thing. We only had the difference in the number of counts in the photon counting method. Here we have two terms in the chi-squared, the difference between the measured and the calculated phase angle, the difference between the modulated measured and the calculated modulation, and then we have the standard deviations on the bottom. In contrast to photon counting, we do not have an exact expression for this, like the number of counts. It's something we determine by experimentation and experience, and we adjust these so we give equal weight to the phase measurements and to the modulation measurements. And it doesn't matter even if we're wrong by an order of magnitude on both, because the chi-squared might go up to 10, but you're always looking for the minimum chi-squared, and it's nice to adjust it to a value near 1, which we did. So let's look at the frequency domain resolution of two lifetimes. In this case, these are two lifetimes that are different by about 4-fold. So these are widely different lifetimes. So here we have the, let's see, the frequency response for the dots are the experimental data from this mixture. So assumption number 1 is that it is a single exponential decay. When we put that into the analysis, we find that the data cannot be fit to single exponential decay. There are deviations in the modulation. There are deviations in the phase. So we can say that the chi-square of 390 is too large, and we can say it is not a single exponential decay. We then increment the model, and we give it 2 decay times. So we let the decay times and the amplitudes float, and we get a perfect fit to a double exponential. So we can recover the 2 initial lifetimes, which were 0.9 and 3.5 nanoseconds. They come out perfectly. And the deviations, which were very large for the single exponential decay fit, are virtually close to 1 for the double exponential fit. So we accept the double exponential fit as explained in the sample. Remember I said last time it doesn't exclude a triple exponential model, but the data are consistent with the double exponential model. And so that's what we accept. I wanted to remind you once again that when you do these analysis, the computer program is going to print out an uncertainty value for the lifetimes and the amplitudes. In my opinion, these numbers are always too small, and the true uncertainty is given by the chi-squared surface, which is the surface that's obtained by varying a parameter value and refitting the data. But obviously it's quite easy to resolve these lifetimes that are different by 4-fold. let's say we use this approach for this trip repressor protein and looking just at the wild type protein. I only put the fit here for the wild type repressor, and we could resolve it into 2 lifetimes of half a nanosecond and 3.3 nanoseconds, fractional amplitudes of 28 and 72%, and the mean lifetime calculated the correct way is 1.4 nanoseconds. So you can see that 200 megahertz was quite adequate for measuring protein tryptophan decays on the nanosecond timescale. Frequency domain instruments are really easy to construct. You can almost build one in your own lab, but it looks exactly like the schematic that I showed you in part 2 for a spectrofluorometer. It has a light source, it has a monochromator to select the emission wavelength. Here it has all of the additions for frequency and polarizers. It has a reference beam, which becomes important, and there's sort of a absolute clock for where the incident light is. The only difference is the addition of an electro-optic modulator, which is put into the light path. Now this is pretty tricky to set up. If you're trying to get an arc lamp through it, it's especially tricky. Can be done, but it's better to use a laser light source. That's much easier. And measurements can be done very quickly. This is because the flux rate is very high, so you can easily measure the whole frequency response in 1 second or less. Just to show you how simple these instruments can be, you can even use a LED light source. So you can take something from your Christmas lights and you can modulate its output and measure a nanosecond decay time with it just by modulating an LED. I'd like to give you an idea of why the phase and the modulation change with the frequency of modulation. And I'm going to do this in 2 slides. They're slightly different, but let's look at this. Let's assume that we had these are all for a 5 nanosecond decay. Let's assume our modulation frequency was 2.5 megahertz. That means peak to peak is 400 nanoseconds. It's pretty clear that 500 nanoseconds is much less than that. It's not going to contribute much to the phase angle because it's simply following the excitation beam. If we go to a higher frequency of 25 megahertz, the phase angle shifts more and the modulation changes, and but now we have 40 nanoseconds between peak to peak, so that's still a lot of time for the 5 nanosecond decay to go away. And if we come down to go up to 250 megahertz, it's only 4 nanoseconds between peak to peak. So clearly the intensity decay is continuing into the next cycle. And this is the origin of the phase shift because a lot of the emission is delayed relative to the incident light. And it's the cause of the decreased modulation. As I said, we are going to do this on 2 slides. So here is another way of visualizing the frequency domain measurements. If you're doing them again with a 5 nanosecond decay time, you can see the decay is over well within the cycle of a 2.5 megahertz signal. If it's a 25 megahertz signal, the decay contributes to the, during one cycle and moving into the next. But if you go up to the 250 megahertz, obviously the 5 nanosecond lifetime is continuing across the 4 nanosecond time from peak to peak, and this is the reason for the large increase in the phase delay and for the decrease in modulation. So I hope these two slides can give you a feeling for why the phase and the modulation change with lifetimes and how that is related to the lifetime of the fluorophore and the frequency of the modulation. So I like to give examples that are a little bit tougher to resolve. And this is the analysis of the time-dependent decay of tryptophan in neutral solution. And I'm mentioning this because this was quite a controversy in the biophysical protein fluorescence literature and meetings, because we were trying to correlate the decays of tryptophan with some structural feature of the proteins. And if the decay of tryptophan itself is complicated, that complicates the correlation. So many of us spent a good deal of time working on the intensity decay of tryptophan. And after very many experiments, we all agreed that it is a double exponential decay with a decay law that looks something like this. Pre-exponential factor of something like 20% for a short decay time and 80% for a long decay time. I think this was not an important controversy because nada, which is the way tryptophan exists in proteins, is a pure single exponential. But let's not get confused by these pre-exponential factors. I wanted to remind you that the contribution in a time-dependent decay to the steady state intensity is given by the alpha tau product, normalized by the sum of the alpha tau products. So when you use the proper equation and calculate what is the fractional component of the short component, it's only 4%. And if you put it on an emission spectrum scale, it's really a very minor component. So the good thing is it shows you how good the frequency domain method is for recovering minor contributions in a decay. And it's probably due to which conformation that tryptophan is in. The bad thing is I think we spend too much time on it at the Biophysical Society meetings. Oh, I just wanted to mention that these two lifetimes are actually very well resolved, which we determined from the chi-squared surface. So, which of course we vary one of the decay times or one of the alphas. So that's an excellent resolution. Now let's look at a global analysis of two closely spaced decay times. And that becomes increasingly complicated. The mixture that we chose is an anthranilic acid and a 2-aminopurine. The lifetimes are different by only 31%. Remember, in the previous example, we had a lifetime difference of 3 or 4-fold. We can anticipate that the contribution of each fluorophore to the decay is equal to the area under the emission spectra. That it is the product of alpha Sub and tau Sub. This particular mixture was measured at 5 emission wavelengths, I believe. And first of all, we showed that if we looked at the either probe alone, they fit perfectly to single exponentials. And if we made a mixture, you could fit that to a double exponential. But what really helped was the global analysis. you can see how close the frequency responses are. That's because the lifetimes are only different by 30%, and I'll show how uncertain the lifetimes were without the global analysis. So let's look at the analysis without the global, the two-component analysis without using all the data. Each single file in the chi-squared surface gives you pretty much the same answer, but they're not quite the same answer. You can see the lifetime shifting around a little bit. So for this closely spaced lifetime mixture, the two lifetimes were quite uncertain, but when we combine the data, all of the measurements, we find that we have a very well-resolved two-component mixture with two well-resolved lifetimes and amplitudes. And for those of you who are a little bit on the mathematical side, you'll notice a difference in the chi-squared equations. In the previous equations at a single frequency, the wavelength never entered because we just measured a single wavelength. In this case, the sum extends over both wavelength and frequency, so it makes it a more complex analysis. And in the old days, when we were dealing with DEC computers, which you probably never even heard of, Digital Equipment Corporation, I don't think they exist anymore, it was a bit of a difficult analysis. There are some very favorable features of the frequency domain method, and I shouldn't call it frequency domain a method for this case, but the phase angles are not sensitive to intensity changes. You can, so this is a measurement of a single frequency, and I'll give you the results first. This is the probe. It's quenched by oxygen. We set up a phase fluorometer in a scintillation vial with a LED light source and the sensor on the other end. And we looked at the phase angle, and then we looked at the phase angles while we waved our hand in between the light beam and the sample. And of course, in that case, the amplitude goes all over the place, but the phase angle is it's extremely flat. And well, this is also why your radios work so well, because you're doing a measurement at a select frequency, so you can get a good radio signal, keeping it constant, auto-adjusting for amplitude. And we'll see later that the single frequency measurements are very useful, especially for something like FLIM, because they can be done so quickly. Perhaps a more relevant example for this talk is a pH sensor, which is a much shorter lifetime, but here we only used a single frequency to do the pH sensing. This is the probe here originally from Molecular Probe. It has two different lifetimes when it's protonated or unprotonated, and it has two different emission spectra and absorption spectra when it's protonated and unprotonated. And you can make what we did is we made a selection. We said, okay, let's look at only the emission beyond this wavelength, because we wanted to get relatively similar amplitudes for the two forms of the probe, and the results are just spectacular. The phase at a single frequency, which we have to use 135 megahertz, changes constantly with lifetime, and it gets shorter because the lifetime gets shorter at the higher pH, and the modulation gets higher at the higher pH. And this can be done in even a very turbid environment, even through skin, if you had to do that. But this is an example of a single frequency measurement. we've always really liked this one. The lifetime distribution, the lifetimes do not have to be multi-exponential. They can also be non-exponential decays. Here you have to use numerical integration of a more complex decay law to get the terms that you need to calculate the total decay law. And as an example of this, I'll use the peptide or protein melittin. Melittin is a peptide from bee venom. It likes to bind to cell membranes. It likes to form aggregates in the membrane, causes holes in the membrane, and that's what you call a bee sting. And we looked at this in various conformational forms. Here we took one case in a solution of methanol and water, and we got a certain decay time. But let's look here at the lifetime distributions. So here, instead of looking at a single alpha value, we allowed the alpha and tau to both vary. And for the random coil state, very sharp double exponential decay. When we get to the alpha helical state, it's a very wide distribution of the alphas and taus. So this really is not a double exponential decay. It's actually something more complex than that. But I would like to give a warning of how difficult it is to do a lifetime distribution analysis, because you always have multiple parameters in there, such as the width of the distributions, and almost always we assume some shape for the distribution. I remember at a meeting one time asking someone, how do you know when to stop the analysis, because it's not always stable? And the individual said, we stop it when we get a distribution that we like. So you have to be careful. These lifetime distributions are very informative, but they can be misleading. Oh, I just want to give you I've always liked this biochemical example of a protein denaturation followed by a frequency domain measurements. So I chose ribonuclease T1 because it's a single tryptophan protein, and it has a very nice single exponential decay when it's in the native state, which suggests that the tryptophan is in a single environment when it's in the native state. But when you denature it, decay just becomes increasingly multi-exponential. So you can follow the denaturation from the frequency response and how the intensity decay changes with the amount of guanidinium hydrochloride in this case. Frequency just like in time domain data, frequency domain data can be distorted by scattered light. We pointed that out in the photon counting lecture. Same is true in the frequency domain. If you have a sample that is scattering, and I'm mentioning this because there are frequency domain instruments that are made without monochromators. They're very convenient instruments to use, but you have to choose, since there's no monochromator, you have to choose the emission filter to make sure you're only looking at the fluorescence and not the scattered light. So if you don't use the emission filter, you let the scattered light go through, which is this case up here, the data are badly distorted by the scattering of the light. If you put in an emission filter, which we did here, cut off all of the scatter, we get a perfectly resolved lifetime for the sample, which looks like it was diphenylanthracene. And the reason I mention this, and I put this in bold red letters, is to remind you to, if you're using an instrument without emission monochrometers or even with emission monochrometers, always measure the emission spectra through the filter that you're going to use. That might seem redundant, but you want to take a filter that you're using in the instrument that you're going to measure the lifetimes with, put it in a regular spectrophotometer, measure the emission spectrum, and be sure that it has cut off the scattered light. There are some modern applications of the frequency domain method, and I'll mention only one. A lot of these are going to be flim, but this I found amazing. We actually did this in around, I forget what year it was, 1990 something. But now I've found it's very popular. If you look in the literature, you'll find a number of publications on lifetime-based flow cytometry. And the basic idea of lifetime-based flow cytometry, excuse me again, is to measure the light as the cells flow through the beam. Typically, that's on the order of 10 microseconds. That can, now you're using a pulse train for excitation, and during the time of when it's at the cell is in the light beam, you can have many, many cycles. I calculated up to 10,000 cycles. The papers don't say that many, but if it's a 10 megahertz pulse train, you get numerous measurements just while that single cell is going through the light beam, and you can analyze that numerically or digitally, and separate the cells based on the lifetime. Here it's only done with microbeads, presented as either the tangent phase angle, lifetime of the bead. But as you can see, you get complete resolution using the beads as they flow through a flow cytometer. So in summary, there are advantages to the frequency domain method. I think one advantage is that there's no limit to the number of counted photons, and this is what enabled the flow cytometry to be done. The flow cytometry lifetime measurements cannot practically be done with time-correlated single photon counting. We'll see later that the frequency domain measurement allows lifetime images to be collected relatively quickly. I'd rate this here, order of magnitude more photons per second. This is just a hard thing to calculate. I've asked an expert in the field, and I've tried to calculate it myself. But there's millions more photons per second in a frequency domain measurement than a time domain measurement. But the frequency domain measurement is really not yet fully developed by industry. I think the reason for this is that the radio frequency preceded the digital technology. So the earliest frequency domain instruments were made with using radio signals rather than pulse detection. And actually, frequency domain instruments have been reported up to much higher frequency, but that requires a change in the modulator and the detector. So that is the end of part 4, and we hope to see you again for part 5. Thank you very much for your attention.